Bismillahirrahmanirrahim. Welcome to the first part of the 15th lecture of Statistics and Probability Theory. Review of previous lecture. In previous lecture, we have studied negative binomial distribution. Negative binomial distribution possesses the four properties. The very first property was that it has two possible outcomes, which is termed as success and failure. This was the first property. And second property was that number of trials, let's say n, are not fixed. They were not fixed because it is assumed that we will keep on doing the trials until we will get the required successes. So number of trials were not fixed. Number 3 was all successive trials are independent. All successive trials are independent, and number 4 was that probability of success remains constant. So these were the properties of the negative binomial distribution, and with the probability mass function, probability x is equal to x minus 1 k minus 1 p raised to power k and q raised to power x minus k, where x is equal to k plus 1 up to so on. So this is the probability mass function of the negative binomial distribution. One more thing which we have studied, that whenever we substitute k is equal to 1 in the probability mass function of the negative binomial distribution, negative binomial distribution will turn into geometric distribution, which is the special case of the negative binomial distribution with the probability mass function is equal to p raised to power 1 and q raised to power x minus 1, where x is equal to 1, 2, so this was the review of the previous lecture. Topic of today's lecture is Poisson distribution. Poisson distribution is a discrete distribution. A Poisson process is the stochastic process in which events occur continuously and independently of one another. Examples that are well moduled as Poisson processes include the radioactive decay of atoms, the number of mutations in a given sequence of DNA, telephone call arriving at a switchboard, page view request to a website, and rainfall. The Poisson process is a collection of random variables where n, depending on t, is the number of events that have occurred up to time t, starting from the time 0. The number of events between time A and time B is given as n of B minus n of A and has a Poisson distribution. So this is a Poisson process. This can be explained more better way from this scenario that this is the initial point, t is equal to 0, and this is the first event occurring, and this is the time between the first event occurring and the initial starting point. X1, X2 represents the sequence of positive random variables with identical distribution. Xn depicts the time elapsed between the n-1th and nth event occurrences. Sn depicts a random variable for the time at which the nth event occurred, and n of t as the number of events that have occurred up to some arbitrary time t. So this is the counting process, and this is called the Poisson process. So this is the introduction of the Poisson distribution. This is the discrete distribution and applies to the occurrences of some event over a specific interval or region of opportunity. Assumption: the rate at which events occur is constant. The occurrence of one event does not affect the occurrence of a subsequent event. So the events are basically independent. Applications of Poisson distribution. It is used in quality control statistics to count the numbers of defects of any item, in biology to count the number of bacteria, in physics to count the number of particles emitted from a radioactive substance, in insurance problem to count the number of casualties, in waiting time problems to count the number of incoming telephone numbers of incoming telephone calls or incoming customers, the number of typographic errors per page in typed material, and we have further many more applications as well for this distribution. Probability mass function of Poisson distribution. The probability distribution of the Poisson random variable x, representing the number of occurrences occurring in a given time interval or specified region, which we usually denote by t, is probability x is equal to e raised to power minus lambda into t, and lambda into t whole raised to power x, where x is the random variable and this whole thing is divided by x factorial, and x is equal to 0, 1, 2 up to so on. So this is the probability mass function of Poisson distribution for a random variable x, and it has one parameter lambda. We note that in binomial distribution we have two parameters n and p. In hyper distribution we have three parameters k, capital N, and small n. And in the case of Poisson distribution we have one parameter lambda, and lambda is basically the average number of outcomes per unit time, distance, area, or volume, where E is equal to 2.71828, T is the time span or space considered, X is the number of successes.